Okay, our next speaker will be Mingyu, who will tell us about quantum simulations of spin-boson models.
Yep, another spin-boson model talk, but this time with trapped ions. And I'd like to also briefly discuss why we think it's an important step towards quantum advantage in this direction. I have to warn you, it's not very empirical-based evidence. It's not like computer sciencey asymptotic arguments, but I hope it's interesting. So if you don't get anything from this talk, you'll still remember that there is a slug that gets energy from photosynthesis. So photosynthesis is not only for plants, it's a fundamental mechanism of nature from which life gets energy. So we want to understand it better. And deep down, it should be a quantum phenomenon, so hopefully quantum simulations can help. We're looking at a small part of photosynthesis, which is this energy transfer in the light harvesting protein complex. So what you see here is the molecular sites in the FMO complex. And each molecular site can have energy excitations. So the excitation can start from the base plate and then hop to different molecular sites in various pathways. And then the energy will be delivered to the reaction center. And you can model this as a Hamiltonian where each state represents which molecular site is excited and solve that, simulate energy transfer. But that's of course not the end of the story because obviously it's a highly open quantum system. If you run a spectroscopy on this molecular system, you see a bunch of these narrow peaks, which are the vibrational modes of this molecular system. They're also pretty high frequency, so they're best represented by quantum oscillators. So full quantum models should capture the electronic states and the quantum vibrational modes, which also appear in models of electron transfer and organic semiconductors. And we're going to use trapped ions. We'll use a long ion chain where the Coulomb repulsion between the ions and the trapping force from the rotating electromagnetic field balance out and create these normal modes of the collective motion of the ion chain. And each normal mode is, we call a motional mode. It's just a quantum harmonic oscillator. So it maps to the boson very well. And if you operate these lasers in this frequency, then you can entangle the qubit states and the motional mode states. And usually it's considered as a recipe for trapped ion entangling gates between qubits. But here we're going to use the motional mode as an active ingredient for quantum simulations. Now finally, ion trap has this all-to-all connectivity, not only between the qubits, but also between the qubits and the motional modes. So the target model we want to simulate eventually is this linear vibronic coupling model, which is a simplified model for condensed phase chemical dynamics. So you have these electronic states and vibration modes, and they can get coupled linearly through this vibronic coupling term. And trapped ions can simulate this model because the molecule's electronic states can be mapped to trapped ion qubits, and the vibrational modes can be mapped to the motional modes. And the all-to-all connectivity, of course, helps because molecular systems will also have very rich connectivity. In this review paper published in Nature Reviews Chemistry, we suggest good linear vibronic coupling model targets for quantum advantage based on literature review and folklores that classical simulation algorithms suffer from these connectivity problems and strong coupling. We suggest that these models would be hard for classical simulations and therefore a good target for quantum advantage, even when we have like 20 to 30 ions in the ion chain. And that's because we also have 40 to 60 motional modes. A caveat for quantum simulation is, of course, that we may require caveat is that they're noisy. So based on numerical simulations, we suggest that the noise parameters may have to improve about 2 orders of magnitude than the state of art, which is a lot to ask. So that's why we want to move beyond the linear vibronic coupling model. And the first thing we see is that these vibration modes in actual molecular systems are very noisy. If you run a spectroscopy, you see all these peak broadenings. And trapped ions motional modes are also noisy. So a natural question to ask is, can we use the analog quantum simulator's noise to simulate open quantum systems, the dissipations in those systems? And that means we want to have good care of these Lindblad operators. So we go back to the spin-boson model in the title. We're going to consider a single spin coupled to infinitely many harmonic oscillators, where the coupling strength to each oscillator is a spectral density value square rooted. And we're going to consider a Lorentzian spectral density because in an actual experimentally measured spectral densities, there are a bunch of Lorentzian peaks. And the line width of each peak, gamma, will represent the dissipation of the corresponding vibrational mode. So the previous proposal of simulating this dissipation was to use sympathetic cooling. If you have an ion chain of multiple species or isotopes, then you can apply laser cooling without destroying the atomic qubit state. And therefore, you can use these Lindblad operators. This was experimentally realized in a very nice work from Rice University. But we didn't have this in our setup, so instead we used this stochastic detuning. So the cite and kick is the name of the operation we use to simulate the coherent part of the evolution, and we're going to trotterize. And in each trotterization step, we're going to add some random detunings. And that will create this Lindblad operator, which is just dephasing. And it turns out this is just equivalent to the noise we call motional dephasing, which is just motional frequency fluctuations. And that is the leading source of errors, at least in our trapped ion system. So in our case, we're injecting and using this motional dephasing, so therefore this should not be a bottleneck for the accuracy of our simulations anymore. So we have this Spin-Boson model with Lorentzian spectral density. And this can be mapped to a single oscillator coupled to a spin, where the oscillator is subject to dephasing. And the line width will correspond to the dephasing strength. And this mapping works out because it turns out these two models have the same two-point path correlation function. And this determines the spin dynamics, at least in the weak spin-path coupling regime. So that leads to this experiment proposal, leading to actual experiments, where that spin coupled to dephase oscillator can simulate the Spin-Boson model in this weak spin-path coupling regime, because the two-point path correlation functions match. So that is this paper. And specifically, we are using a 7-ion chain. We're going to do operations only on the center ion. And we're going to use 3 of the 7 motional modes to represent the spectral densities. So this is the experimental protocol. We first prepare the qubit in the 0 state, cool down the motional state, and then apply kick operations with random phase. And if we average over many random instances, this will effectively generate a thermal state of the desired average phonon number. Then we simulate the coherent evolution, but then we add this random detunings, and that will tune the spectral line width of the path. So these are the first experimental results. What you're seeing is just the qubit 0 state population dynamics. And as you increase the average phonon number, you see that this revival amplitude decreases. And it matches very well with the theoretical predictions, especially when you consider the dephasing noise of the hardware. And next, we can simulate the spectral line width as well. This is interesting to me because if you follow this t equals 10 line, you see a phase flip from pi to 0. So that means we're seeing this crossover from underdamped to critically damped to overdamped dynamics. So that's good. And we can go beyond using only one mode. So we can use 3 modes to simulate this kind of spectral density, assign each peak a motional mode, and give random detunings to create these line widths. And again, we see a really good match between theory and experiment, even when our experiment time is about half the motional coherence time. So this really shows that motional dephasing, the leading source of errors usually, is not the bottleneck for accuracy anymore. We're using it. I'm going to skip this, but we simulate some densities related to Leggett's model. And then finally here, we're adding some detunings to the spin, and therefore we're simulating the vibration-assisted energy transfer. So if the vibrational mode frequency meets the resonance condition, the transfer happens. If it's not, it's suppressed. Depends on the temperature. And also finally here, what you're seeing is as we increase the spin-path coupling strength kappa, the spin dephase oscillator model starts to deviate from the original Spin-Boson model. So that sounds alarming. Maybe dephasing was not a good choice at all. I should have used the original sympathetic cooling approach. But then I would like to remind you here that Spin-Boson model is not our end goal. Our end goal is to simulate actual condensed space chemical dynamics phenomena. And if you compare all these different decoherence processes that happen, actually vibrational dephasing is stronger than the vibrational relaxation. It happens at a shorter time scale. So we need both ingredients, basically. To sum up, as we scale up the number of spins and the motional modes, there is a clear path towards quantum advantage. The problem was noise, of course, but then it turns out we can actually even inject and use the noise to simulate the dissipative part of the open quantum system models. And these were experimentally realized in these 2 works. So these are important ingredients for quantum simulation towards quantum advantage. And hopefully this dialogue between chemistry and quantum simulations will unlock models of nature that better describe all the processes that happen in chemical dynamics. So that would be very exciting, and I would like to thank my collaborators and the funding agency.